Hello students, welcome to the amazing platform of Physics Wallah. Today we are going to have a one-shot revision on the chapter solutions. I hope all of you are super excited. I am super excited. Today we are going to discuss about the conceptual part, that is the theoretical part. In the next session we will be covering all the numerical part of this chapter. So let's start the session. So first of all, if we talk about solutions, what is the solution? Yes, the first and the most important question that comes in our mind is, what is solution? Okay, now what you have to imagine is a lemonade. Yes, you drink lemonade? Yes, ma'am. What is that? That is a solution. So in this chapter, we are going to discuss only and only about homogeneous solutions. What are we going to discuss? Ma'am, we are going to discuss about homogeneous solutions. What are homogeneous solutions? The ones in which there is no different layer, right? Solute is absolutely soluble in your solvent. That is known as a solution. So now let us discuss about solution. Solution consists of two major components. Every solution has two major components. Let us discuss about that. If you talk about solutions, then it has solute and it has solvent. Okay, now the next question that comes in our mind is, how many solutes we can have, how many solvents we can have, or we can have only one solute and one solvent. So we are going to discuss about that. So first of all, let us see the definition. The definition says that a solution is a homogeneous mixture. It is a homogeneous mixture. Homogeneous mixture, we just discussed that homogeneous mixture is the mixture where there is no different layer. Your solute is absolutely soluble in your solvent. Yes, of two or more than two components. Now, ma'am, you said that in a solution we have only solute and solvent. Why are they saying that it has two or more than two components? Because, my dear students, now we are going to discuss about how many solutes and how many solvents we can have in a solution. So let us start discussing about that. Now, a solution has major two components. One is known as solute and the other one is known as solvent. Okay, yes, a solution has only one solvent but one or more than one solute. How can we understand this? Now here you have to again think of lemonade. Yes, whenever you think of preparing a lemonade, what do? You take water, you dissolve sugar in it. Yes, you also dissolve salt in it. Yes, so here what is this? The water is your solvent and the sugar is your solute. Also the salt is your solute. So from this we understand that you can only have one solvent. You cannot have two waters, right? You can only have one water, but you can have more than one solutes. Yes, ma'am. So that is the important part where you have to pay attention, that you can only have one solvent, but one or more than one solute. Yes. So I hope you get this. This is very important, my dear students. So you can mark it as important. Okay. Next. Now, whenever we have different number of solutes, how do we classify the solutions? There should be some different names. Yes. So here are the different names. Now, whenever you talk about solvent, you will have only one. When you have one solvent and you have one solute, total components are two. Yes, ma'am. 1 plus 1. 2. And whenever you have two components, you call it as a binary solution. It is a binary solution. Okay. Perfect, ma'am. Next, you can have only one solvent. Yes. But you can have two solutes. Yes, ma'am. So here is 2. So total number of components are 3. So ma'am, here the total number of components are 3. And we call such a solution as tertiary solution. Tertiary solution or ternary solution. Ternary solution is a better word, so we'll call it as ternary solution. Next, you can have again one solvent. Yes, ma'am, but you can have, my dear students, 3 solutes. And whenever you have 3 solutes, you have total number of components 4, and you call it as a quaternary solution. Quaternary solution. No problem? No, ma'am. So perfect. This is how you classify the different types of solutions. Now, What if in our question we are not given that it is a ternary solution or a quaternary solution? Then my dear students, by default you have to take it as a binary solution. Okay, whenever it is not mentioned in the question, just consider it to be a binary solution. You have one solute and one solvent. So it is written here. If nothing is mentioned, we can assume a binary solution, and most of the cases are binary solutions. Perfect. Next, now a solute is dissolved in a solvent. It forms a solution. Yes ma'am, we understand that. And now how can you classify solution, my dear students? Class solution has a different types of concentrations. What is concentration? Actually concentration just tells you about that how much solute is dissolved in a solvent. So now here, how can I explain you that? Just understand by, if I tell you that my height is 6. My height is 6. So if my height is 6, let us write it as, if my height is 6 feet. Okay, bacha? Yes, ma'am. My height is 6 feet, or I could say 180 centimeters. Right? Yes. So is my height changing? No, ma'am. Your height is not changing. But the way I am expressing my height, it is changing. Yes. So same way, my dear students, whenever you talk about concentration term, you are actually talking about that how much solute is dissolved in a solvent. Right? And you are just expressing it in different ways, and those different ways are known as concentration. Right? Like if I tell you that I have 5 grams of a solute dissolved in 100 grams of solvent, that is one particular type of concentration term. Next, if I say I have, let us say, X moles of solute in some specific moles of solvent, so that is a different type of explanation. That is a different type of concentration term. So it basically talks about the same solution. It basically talks about the same solution but in a different way. So concentration terms are nothing but just the expression of how much solute is dissolved in a solvent. Right? Yes. So here it is. Solute is the reactive part and the solvent provides the medium for the reaction. Now you have to understand this. Whenever you have a solvent, you have water. Right? If you dissolve sugar in it, it tastes sweet. Yes, ma'am. And if you take water, that is your solvent, and you dissolve salt in it, it does not taste sweet. Right? It has a different taste. So here, my dear student, what is the difference? Solvent is the same, but the taste is given by what? Solute? Yes, ma'am. So my dear students, from here we can say that solute is the reactive part. Solute is the reactive part. Solvent just provides a medium. So yes, we understand this line that solute is the reactive part and solvent provides the medium of the reaction. So the most important part would be solute, because that is the reactive part, right? That decides what is the taste or what will be the nature of your solution. Right? Perfect. Next is the amount of solute in a solution is represented by the concentration of the solution. We just discussed it. Yes. Now we are going to discuss different types of concentration terms. You are going to love this part because most of the numericals are asked from this part and it is the most easy part of this chapter. So let us start this. Next, concentration. It is the measure of the amount of solute in the solution. Again, the same thing, my dear students, that how much solute is present in a particular amount of solution. It is just the measure. You just express it in different ways. Sometimes you express in grams, sometimes you express it in moles, or sometimes you express it in kgs and different types of expressions, right? So we are going to discuss about all those expressions. So let us start the session. Now, molarity. The first concentration term and the most important concentration term is molarity, and it is represented by capital M. It is represented by capital M. Okay. So this is the most important thing which you need to understand. Perfect. Next, what is molarity? I'll tell you the definition. First, you have to understand in the layman language. What is molarity? Actually, molarity tells you that if you have 1 liter of solution, understand this, you have 1 liter of solution. Okay? Yes, ma'am. You have 1 liter of solution. Now, how many moles of solute are you dissolving in 1 liter of solution? That is what is known as molarity. If I have a solute and I dissolve 1 mole of it, right? Then I would say I have 1 mole of solute in 1 liter of solution. So the molarity would be equal to 1 molar. Okay. Next, if I dissolve 2 moles of that same solute in 1 liter of solution, then I would say that molarity of the solution is 2 molar. So basically it just explains you that if you have 1 liter of solution, then how many moles of solute are present in it. Perfect? Yes, ma'am. Now you can read it. It is the number of moles of solute present per liter of the solution. Right? Now, if you have to write a formula for it, what would be the formula? Let us understand that. If you write the formula, then bacha, molarity would be equal to how many, that is moles of solute, right? Divided by volume of solution in liters, right? Yes, ma'am. This is the major formula which you need to understand about molarity. Okay, now you can understand this formula. There is no issue. We will practice questions on it in our next session. Okay, now what other thing we need to know about molarity? If I tell you that I have, let us say 3 molar NaOH solution. Okay, ma'am said you have 3 molar, capital M means molar, NaOH solution. What does this mean? This means that you have, my dear students, 3 moles of NaOH, because NaOH is your solute here. So you have 3 moles of NaOH present in 1 liter of solution. So whenever you are given something in this form, 3 molar NaOH solution, 3 molar KOH solution, 3 molar H2SO4 solution, you will read it as you have 3 moles of NaOH present in 1 liter of solution. Now from here you can derive hundreds of things, right? You can see you have 3 moles of NaOH. Now if I ask you what is the mass of NaOH, you know that number of moles into molar mass of NaOH will give me the total mass of NaOH. Yes, what is the molar mass of NaOH, my dear students? 23 plus 16 plus 1, which is 40. So ma'am, this is 40. So 3 into 40, which is equal to 120 grams. So you have 120 grams of NaOH. So my dear students, decoding this particular part gives you so many informations which you can use in your numericals in hundreds of ways, which we are going to practice in our next session, right? Yes. So this is the beauty of molarity. I hope you understand this. Now, your homework would be, if I ask you that you have 4 molar H2SO4 solution, right? Yes, ma'am. Now, I am also giving you the density of the solution, which is equal to, let us say, how much? I would say 1.2 grams per milliliter. Okay, so this is your homework question, my dear students. You have to tell me mass of H2SO4. What is the mass of H2SO4 in this solution? Okay, ma'am. What is the moles of H2SO4 in the solution? Moles of H2SO4 in the solution. And also, you are going to tell me what is the mass of solution present in it. What is the mass of solution present in it? Okay, perfect. So these 3 are your homework questions. Just understand this, decode this expression, use this density. I am giving you a hint, my dear students. You have to use density is equal to mass by volume. You can use this expression and you can calculate all the 3 parts. Okay, so do comment down your answers and I'll definitely check them. Perfect. Next, my dear students, this was molarity. Now the next concentration term is molality. Ma'am, just now we discussed molarity. What is molality? My dear students, you can see that there is just a difference of one word, which is L. That was molarity and this is molality. But there is a whole lot of a difference in the expressions of both, right? Yes, molality is defined by small m. Always, whenever you see small m, just understand that it is talking about molality. Okay, now what does molality define? The same way we understood molarity, we are going to understand molality. What does this mean, my dear students? You have, again, you will take a container, and you will take solution here. I have a solution. Let us say we have a solution. Okay, solution is made by solute and solvent. So first of all, let us consider it as a solvent. Now, I am telling you that you have 1 kg of solvent. Here you will talk about the mass, 1 kg of solvent. Here you will talk about the mass and also that of solvent. In case of molarity, you talked about the volume of the solution, but here you're going to talk about the mass of the solvent, and that is 1 kg. It is fixed. Now you add the solute. Now you add solute. Let us say you added 1 mole. So if you add 1 mole of solute, then molality would be defined as how many moles of solute are dissolved in 1 kg of solvent. So if I ask what would be the molality of this solution, you would say, ma'am, 1 mole, right? Yes. Next, my dear students, if I say that I added 2 moles of solute in 1 kg of solvent, then what would be the molality? Ma'am, molality would be 2 molar, right? Yes. Now you can read the definition. Yes, it is the number of moles of solute present per kg of solvent. The important thing which you need to understand is per kg of solvent. It is not solution, it is solvent, my dear students. Don't get confused. Okay, now we are going to derive the formula of molality. Okay, now what would be the formula of molality? Moles of solute. Yes, ma'am. So here will be moles of solute divided by mass of solvent in kgs. Yes, ma'am. So here will be mass of solvent in kg, right? Yes. So this would be the formula. This would be the formula of molality. Easy? Yes, ma'am. Easy. So we are going to practice questions on this in next session. So you have to revise this and come to the next session. Perfect. Now, if we are given some expression, then how are we going to decode it? We have to understand that as well. Yes. So if I tell you that you have 3 molar, small m denotes molar, 3 molar NaOH solution. How are we going to decode this? Okay, now 3 molar NaOH solution means that you have 3 moles of NaOH, because here NaOH is what? NaOH is my solute. Yes, so I have 3 moles of NaOH present in 1 kg of solvent. 1 kg of solvent. Now, my dear students, here I want to tell you one more, a very minute and very important expression which will help you in solving many questions. Whenever you are given, let us say example, you are given aqueous NaOH solution. NaOH solution, or you are given aqueous H2SO4 solution, any type of aqueous solution. Whenever you are given any type of aqueous solution, my dear students, this aqueous represents that your solvent is water. Your solvent is water. Whenever you are given aqueous solution of any kind, your solvent would be water, and here solute would be NaOH. Solute would be NaOH. Similarly, here aqueous means solvent is water and solute is H2SO4, right? Yes. So here there is nothing is given here, so we can't decide that what is a solvent, but we can understand that NaOH is our solute. Okay, there is no information is given about your solvent, but solute is NaOH, that is final. Perfect. But if I add aqueous here, then you know that your solute is NaOH, and your solvent is water. So if aqueous is written, we can say 3 moles of NaOH are present in 1 kg of solvent, and we know the solvent as well. Which solvent? It is water. Right? Yes. So this is how you are going to decode the informations. Right? Yes. I hope you understand this, and this is a very important part. Perfect. Very good. What is our next concentration term? Next concentration term is mass by volume percentage. Now let us talk about mass by volume percentage. What does this mean? You are going to discuss about mass by volume percentage. You are going to discuss about mass by mass percentage. Also, you're going to discuss about mass by volume percentage, volume by volume percentage. Yes. So we are going to discuss about all three, and you just need to understand that in all these mass by mass, mass by volume, or volume by volume, you always take the mass in grams. Again, just understand this. Whenever you are talking about the percentage wala part, what is the importance? You are going to take the mass in grams and you are going to take the volume in milliliters. This is the most important part. Okay. Now I will just make you understand this. Mass by volume percentage basically, or you could say it as volume percentage as well. My dear students, mass by volume percentage is mass of solute present in 100 ml of solution. Okay, so basically this tells that if you have 100 milliliters of solution, then how much mass of your solute is present in grams. Okay, let us say, I'll give you an example. I have 500 ml solution. I have 500 ml solution in which I have 50 grams of solute. Right? Yes. Now I want to know what is the mass by volume percentage of this particular solution. So you know that mass by volume percentage tells me that how many grams of your solute is present in 100 ml of solution. Now you have 500 ml of solution. In 500 ml of solution, you have 50 grams of solute. Right? Yes. So if you have 1 milliliter of solution, then how much you will have? 50 upon 500 grams of solute. Yes, ma'am. Basic beta unitary method. Yes, ma'am. Next, if you have 100 ml of solution, then you will have 50 upon 500 into 100 grams of solute. Right? Yes, just solve it. This is 10, this is 100, and this is 100 and 100. So, ma'am, basically 10 grams of solute. So now you can say that in 100 ml of solution, you have 10 grams of solute. So what will be the mass by volume percentage? Ma'am, 10. The mass by volume percentage would be 10. So this is one method of solving this question using the unitary method. But we need a formula as well. So let us derive a formula also. Yes, ma'am. What would be the formula, my dear students? Mass by volume percentage would be equal to mass of solute in grams. This is the most important part. It should be in grams. Right? Divided by volume of solution. Okay? Volume of solution in milliliters. This is important, my dear students. Don't take the volume in liters. All your calculations would be wrong, right? Yes. Now, if you use this particular formula for the same question, if you use this particular formula for the same question, that you have 500 ml of solution and 50 grams of solute, what would be the mass by volume percentage? Just put the values. 50 grams of solute, 500 ml of solution. So, mass by volume percentage would be 50 grams of solute, 500 ml of solution. Did we write into 100? Yeah. Okay. Here 100 also. Yeah. We are calculating percentage, so we have to multiply by 100. So here it will be 100. Right? Again, my dear students, this would be 10 grams. 10%. Perfect. So this is how you calculate mass by volume percentage. Okay. Now, how will we decode? Yes, ma'am, expression. If we are given an expression, how are we going to decode it? We are going to learn that as well. If I tell you, my dear students, that you have 10 mass by volume percentage of aqueous NaOH solution. Okay, we are going to discuss only and only about NaOH solution so that you can understand that we are talking about the same solution but just in a different way. Now, if you see that, you would say that you have 10 grams of your solute. And what is your solute? NaOH. You have 10 grams of NaOH. I'll write here solute as well. And it is present in 100 ml of solution. And it is present in 100 ml of solution. Now, if you are given density, you can find the mass of solution, you can find the mass of solvent as well, and you can find hundreds of other things, right? If you know how to decode this information, you can do all the numericals yourself. So learn this, not learn this, I would say just understand this, how to use this concept so that there's never any problem and there's nothing that you cannot do, right? Yes. Perfect. Next, my dear students, next is mass by mass percentage, and I hope you can yourself tell me that what will be the formula of this concentration term. Mass by mass percentage, ma'am. Mass by mass percentage would be equal to mass of solute divided by, in grams, divided by mass of solution in grams into 100. Easy. Yes, ma'am. Right. You can understand this. It is the grams of solute present per 100 grams of solution. Perfect. Now, again, we are going to decode the information as well. Expressions. If you are given 10% mass by mass aqueous NaOH solution, how are we going to read it? Very easy, ma'am. I think you can also answer it. Just pause the video and answer yourself. This will be, ma'am, 10 grams of NaOH solution. 10 grams of NaOH solute, right? Yes, this is your solute and it is present in 100 grams of solution. Right? Now, my dear students, if you are given density of the solution, you know the mass of the solution, you know the density of the solution. Can you calculate? Can you, my dear students, calculate the volume of the solution? Yes, ma'am, we can calculate the volume of solution. Right? There's no issue. Perfect. Next, my dear students, if you are given mass of the solute, can you calculate the moles of solute? Yes, ma'am, we can calculate. If I tell you that in this particular question, you have to calculate the molality. Calculate molarity. Calculate molarity. No, let's first calculate molality. That would be much easier for you, and then we'll calculate molarity as well. Okay? You are supposed to calculate the molality. For molality, what do I need? Molality means, ma'am, small m, and it means that you need moles of solute divided by mass of solvent in kgs. Yes, ma'am. Perfect. So you need moles of solute. You have mass of solute, so you can calculate the moles of solute. Moles of NaOH would be given mass, which is 10 divided by molar mass, which is 40. So, ma'am, number of moles are 1 by 4. Okay? No issue. Perfect. So we'll write it here as 1 by 4. Divided by, my dear students, you are supposed to calculate the mass of solvent in kgs, right? Now see, you have 100 grams of solution and you have 10 grams of solute. We know that mass of solution is always equal to mass of solute plus mass of solvent, right? Yes. Then mass of solvent would be equal to mass of solution, which is 100, minus mass of solute, which is 10. This is 90 grams. So now you have mass of solvent in grams. You just convert it into kgs and put it in here. So it is 90 grams. So ma'am, 90 by 1000 would be in kgs. And now this, using this, you can calculate the molality, right? Similarly, my dear students, if you were asked to calculate the molarity, how would you calculate the molarity? Ma'am, it is very easy. We had to find moles of solute and divided by the volume of solution in liters. So, how to calculate the volume of the solution if you are given the density of the solution? You have mass of solution 100 grams. If you were given in the question the density of the solution, you could calculate the volume of the solution. Yes, ma'am, that would be in milliliters. Just convert it into liters and you could find out the molarity as well. We will practice questions on this, but this was just a glimpse of what are we going to discuss in the numerical part. Okay, perfect, very good. Next question, my dear, next concentration terms, my dear student. It is volume by volume percentage. How are we going to calculate this? Let's see. Ma'am, now we can understand everything. Volume by volume percentage means that how many milliliters of your solute is present in 100 milliliters of solution. This is so easy. And if you are supposed to write the formula, you can write the formula yourself. Volume by volume percentage would be equal to volume of solute in milliliters divided by volume of solution in milliliters into 100. This would be the formula. And how are we going to decode the expressions? Let us write that as well. Right, ma'am, if you are telling us, if you tell us that you have, what is this? Okay. If you tell us that you have 10% volume by volume aqueous NaOH solution. Yes, just decode it, my dear students. You can do this yourself. Ma'am, 10%, so 10 milliliters of solute is present in 100 milliliters of solution. Right? Yes. So this is so easy. Very easy. I hope there is no issue. Perfect. Next. We are going to talk about the next concentration term, which is mole fraction, and it is one of the most important concentration term you are going to use in your whole liquid solutions chapter. So just focus on it. Okay? Yes. If you talk about mole fraction, my dear students, it is represented by X. Some people represented by X, some people represented it by chi. That's not an issue. This is just a representation. It is all on you how you want to represent it. Now, what does mole fraction mean? You have to understand first that it has a word fraction. So, my dear students, it will be a fraction. Always it will be a fraction. Okay. Now, let us consider I have a solution. I have a solution which has two components, A and B. One is solute and one is solvent. Okay. Perfect. Let us say we have Na moles and Nb moles. Now, what would be the mole fraction? Each and every component has its individual mole fraction. It is their specific value. Okay. So, if I talk about the mole fraction of A, right? So, let us write it here, mole fraction of A. Okay. So, what does this mean? We can represent it as like this. What will be the mole fraction of A? That how many moles of A are present in the whole solution. So how can you represent it? Moles of A divided by the total moles present in the solution. So you have two components. So first moles of A are Na and moles of B are Nb. So if you are calculating the mole fraction of A, then ma'am, this will be moles of A divided by, my dear students, total moles present in the solution. How many moles are present? Na plus Nb. So this will be Na plus Nb. So this is the expression for mole fraction of A. Similarly, you can calculate mole fraction of B as well. So mole fraction of B would be moles of B divided by total moles present in the solution. If you had a third component, let us say if you had a third component which was C component and its moles would be Nc. Then, my dear students, you would have to write here Nc, Nc, and then mole fraction of C would be moles of C divided by total moles, that is Na plus Nb plus Nc. Okay. Now, another important thing, that all of the mole fractions are fractions, right? If you add all of them, you will get one value, because fraction is out of 1. Yes, ma'am. So add all these. Let us say this is 1, this is 2, and this is 3. What are you supposed to do? Just add all the 3. Okay. If we add all the 3, then XA plus XB, mole fraction of A plus mole fraction of B plus mole fraction of C would be Na by Na plus Nb plus Nb by Na plus Nb plus, okay, plus Nc divided by Na plus Nb plus Nc. Add all the three. You will get Na plus Nb plus Nc divided by Na plus Nb plus Nc. Right? This is equal to 1. So what do we understand? That if we have mole fractions of all the components present in a solution, then sum of the mole fractions of all the components will always be equal to 1. Right? Yes. So this is the beauty of a mole fraction. If you know the mole fractions of any two components, if you have three components in your solution and you know the mole fraction of two components, you can definitely calculate the third component's mole fraction just by subtracting them from 1. Right? Yes. So this is how you calculate the mole fractions, and you're going to use it in hundreds of ways in this chapter. Perfect. So we understood this. Is there anything other than this? No. It is the fraction of total number of moles. Yes, ma'am. And the sum would be always equal to 1. Perfect. So here we are here with the other concentration term. What is the other concentration term? It is, my dear students, parts per million, and it is used widely nowadays. What does parts per million mean? And parts per million means that it is exactly same as percentage, my dear students. What you used to calculate is that in 100 grams of solute, how many grams of, in 100 grams of solution, how many grams of solute is present, right? Similarly, in ppm, you calculate that in 10 raised to the power 6 grams of solution, how much grams of solute is present. Exactly like percentage, just the difference is now you are going to take the mass of your solution as 10 raised to the power 6 grams, right? Yes. So it is the number of grams of solute per 10 raised to the power 6 grams of solution. So if you write the formula, what would be the formula? ppm would be mass of solute, again my dear students, in grams, divided by mass of solution in grams into, this time, 10 raised to the power 6. In percentage, we calculated it out of 100, so we multiplied by 100. Now we are calculating from 10 raised to the power 6, that is 1 million. So this is 10 raised to the power 6. Right? Now let's decode the expression. What would be the expression, my dear students? If I tell you that I have 3 ppm of, let us say, I have 3 ppm of Cl2. I have 3 ppm of Cl2. Okay, so how are you going to calculate it? How are you going to decode it? You would say that you have, okay, let us say NaOH solution. Again, we are going to talk about NaOH solution only because we used this expression, so we are not going to cheat it, right? Yes. So 3 ppm of NaOH solution means that you have 3 grams of solute in 10 raised to the power ppm per million. So 10 raised to the power 6. Yes. So 10 raised to the power 6 grams of solution, right? Yes. So it is exactly same, my dear students. Just don't get confused. Every place where in percentage you used 100, you have to use 10 raised to the power 6. Everything is same. Only you are calculating out of 1 million and there you were calculating out of 100, right? Yes. So I hope you have understood all the concentration terms. They are widely used and you get questions of interconversion of these. Now, if you know how to decode the information, you can calculate each and every concentration term. You are never going to have any problem. Okay? Yes, ma'am. Perfect. So, next, now we are going to talk about, my dear students, vapor pressure. What is vapor pressure? Right? So, let us talk about vapor pressure. What is vapor pressure? How are we going to understand this? For this, you have to imagine, my dear students, imagine you have a bowl. You have a bowl and you have water inside it. Okay. Now, when the water boils, my dear students, when the water is heated, what happens? You see some vapors going outside. You see some vapors going outside. Just understand this. This is a closed container. Okay, I am talking about a closed container because if it was an open container, the vapor would have gone into the atmosphere. Okay, so now we are going to talk about a closed container in which you can see some vapors because of the liquid, because of the water inside it. Okay, yes. So this vapor, my dear students, exerts some pressure. This vapor exerts some pressure. This is the basic idea behind it. I'm going to make you understand the complete process of vapor pressure and the process of boiling point, right? Yes. So let us move forward. Now, for this, what you have to do? You have to come with me to a jail. Have you ever been to a jail? No. No student have been to a jail, but at least you have seen movies. Yes, ma'am. And you all have seen various thieves and you have seen various jails, right? So now we are going to go into a jail. Yes. So my dear students, what you have to imagine is, this is your jail. This is your jail. Basically, this is water. This is water. Okay. Yes, ma'am. And this is a closed container, my dear students. Imagine this is a closed container and this is water. Now, imagine this water to be a jail. This is a jail. Okay. Now, this jail has various particles. Let us say it will have particles on the surface. Yes, ma'am. And my dear students, it will have particles in the bulk as well, right? What is bulk? Something inside is bulk and something on the surface is known as surface, right? Yes, ma'am. So you have various particles in the bulk and you have various particles on the surface. Now, imagine this one particular particle. Okay, we are taking this one particular particle. It is inside, it is in the bulk. Okay, so basically it is in the jail. Okay, now you see that this experiences a force from this side. There will be many thieves will be present there. So let us say one thief was just pulling him towards himself. Okay, the other thief pulled him from this side. Yes, ma'am. The other thief pulled it from upside and the other thief pulled him from outside. So what we can understand that when somebody is in the bulk, it experiences equal forces, right? If I stand here and somebody is trying to pull me from this side and somebody is trying to pull me from this side as well, so I will experience an equal force as long as they both are applying an equal force on me. Okay, so I'll be stable, right? I don't have any energy. No, everyone is pulling me equally. So this particular particle is stable. This particular particle is stable. So I can say that this particular particle is stable. It has very less energy. Okay? Yes, ma'am. No issue. You understand this. Now, let us think it about as a thief. If he was a thief, he was inside the jail. He has not seen the world outside. So he doesn't have any urge of going outside. Right? Now understand the thieves on the surface or the particles on the surface of your liquid. Okay. Now, if you see this particle on the surface of the liquid, this particle will pull it towards itself. This particle will pull it towards itself and downward force will also be present. But will there be any force from upside? No, ma'am, because there is nothing present. There is no other particle present in the outside. Yes, so this particular particle, my dear students, is unbalanced. Yes, ma'am. So it will have some kind of energy. Yes, ma'am, because it is experiencing unbalanced forces. Yes, so what will we say? That it is unstable. Why? It is unbalanced. Yes. If it is unstable, then it has a lot of energy. Yes, ma'am. So you can say that it has energy. It has energy. Okay. Now you have to understand it by the concept of thief. Now, if he is a thief or he is a prisoner and he is sitting on the surface, he is sitting on the doors of the jail. He can see the outside world. He can see people enjoying. So he will have an urge of going outside. As compared to the people who are inside the jail who have not seen the world outside, right? Yes. He will have an urge of going outside. Yes. Similarly, these all surface particles can see the outside world. All these surface particles wants to go outside and enjoy the free world, right? Yes. So they all are unbalanced. They all have energies as compared to the particles inside. Yes, ma'am. So whenever they will get a chance, the particles on the surface will just leave the jail. Yes, they will leave the jail and they'll just go outside in the outside world. Now imagine that this particular particle has energy. Yes, ma'am. It just got a chance and it just went outside. Okay. If he goes outside, now he's in the free world. He's like, what should I do? I should enjoy this. I should do this. I should do that, right? He wants to do everything at the same time. So he has a lot of energy and he is just running. So he's running like this, like this, like this, like this, like this, like this, right? You understand this? So now whenever he strikes the walls of the container, he exerts a pressure. Now you have to understand it according to the water molecule concept. It was unbalanced. Yes, it had energy. It just left the surface. Whenever it left the liquid surface, it just got converted into a vapor. And when it got converted into a vapor, it will strike on the surface of the walls of the container and it will exert some pressure. Yes, ma'am, it will exert some pressure. And my dear students, what can you say? Ma'am, it is exerting some pressure, right? Now my question is, will only one particle exert pressure? Will only one particle leave the surface? No, all these particles can leave the surface, right? Yes, so at some particular temperature, many of the particles leaves the container and what does they do? They strike the surface like this and exert some pressures. Okay, now my dear students, now the policemen, they will also come to know that yes, some prisoners have left the jail. They'll go and they'll catch them. Now some police people will grab them and they'll take them back, right? Now, when they will grab them and they'll take them back, the others would leave, right? So, we can say that there will be equal number of people going outside the jail and equal number of people coming inside the jail. There will be an equilibrium. So, at some particular temperature, there will be an equilibrium where equal number of molecules will be going in the vapor phase and equal number of people will be coming inside the liquid phase, right? So, this particular part would be known as when there will be an equilibrium, that is when equal number of molecules are getting converted into the vapor phase and equal number of molecules are getting converted into the liquid phase, that particular part would be known as a saturated vapor or saturation point. Okay? That would be known as a saturation point when there will be an equilibrium between the vapor and the liquid phase. Okay, and when this equilibrium will be attained, the pressure exerted at this point is known as, my dear students, the vapor pressure. So what would be the vapor pressure? The pressure exerted at the saturated condition is known as the vapor pressure of that particular liquid, and vapor pressure is constant at a particular temperature. If you are taking this whole process on one particular temperature, then the vapor pressure for that particular temperature for a liquid would be constant. I hope you understand this. Perfect. Now let us read about it. Okay. Vapor pressure is the maximum pressure exerted by a vapor in equilibrium with the liquid. When is the equilibrium attained? When equal number of molecules are going in the vapor and coming out of the and coming into the liquid as well, right? So I hope you understand this point. Next, vapor pressure represents the pressure of the saturated vapor. My dear students, the saturated vapor is when there is an equilibrium attained. Yes, and that is the pressure you call as vapor pressure. Next, vapor pressure depends only on the temperature and the nature of the liquid. Yes, at one particular temperature, you have one particular vapor pressure. If you increase the temperature, vapor pressure would increase. But if you are talking about a particular temperature, then its vapor pressure for one particular liquid would be constant. Perfect. I hope you understand the third point as well. Fourth, vapor pressure does not depend on volume of the container or amount of the liquid. It does not depend on any other thing other than just the temperature and the nature of the liquid. For every other different liquids, you will have different vapor pressures at different temperatures. So vapor pressure only depends on temperature and the nature of the liquid. Perfect. You got this point. Now we are going to talk about the vapor pressure of a solution. Okay, how are we going to talk about it? We are going to talk about the Raoult's law. What is Raoult's law? Let us understand that, my dear students. Now, if you consider a normal solution, let us say you have this closed container, and you have only and only one liquid solvent, let us say A. You have only one liquid, which is A. Okay. Now, what would be the vapor pressure? Ma'am, let us say PA naught is the pure vapor pressure of A, right? PA naught is the pure vapor pressure of A. This is the pressure that PA exerts at some particular temperature T. Okay, perfect. Now, my dear students, let us take the same container, and let us take another component B. Now I am taking another component B. Let me represent it by blue color. Okay, so this is B. Now, if I ask you what would be the vapor pressure of this, ma'am, you would say that the vapor pressure would be PB naught. This would be pure vapor pressure of B. Okay. Now, what am I asking you? These both are volatile. What does volatile mean? Any component which can exert vapor pressure is a volatile component, and if any component cannot exert vapor pressure, does not form vapors, then that is a non-volatile solute or solvent. It can be anything. Okay, that is non-volatile. Perfect. So we got the basic meaning of volatile, and here they are saying that both are volatile. So A is also volatile, B is also volatile. It also has a vapor pressure. It also has a vapor pressure. Okay. Now, what am I saying? That let us add both A and B in one container. Now, if you add both A and B in one container, let us say here. Okay. So now you have A plus B. Okay. So A was white color, and B was blue color. Okay. So I'm representing them as different. Okay. Now, if I ask you that what will be the pressure of this container, what would be the vapor pressure here? Now you can say one thing. That, ma'am, PA. What would be PA? It would be the partial pressure of A, because now it cannot be equal to PA naught. And PB will not be equal to PB naught. Now the question is why? Because, my dear students, what was happening here? Here all the particles were A, right? Here all the particles were B. That is the reason they had PA naught and PB naught pressures. If you are mixing them, then you will have some particles of A and some particles of B on the surface as well. Now, if you have A and B, both the particles, they will hinder each other's vapor pressures. Yes, ma'am. That is the reason that my dear students, that PA cannot be equal to the pure vapor pressure of A, and PB cannot be equal to the pure vapor pressure of PB, right? And total vapor pressure here would be equal to PA plus PB. Okay, this is the basic idea of how we calculate the vapor pressures. Okay, now we are going to go further. I hope you understand this part, that why PA is not equal to PB naught, and why PA is not equal to PA naught, and why PB is not equal to PB naught. Perfect. Now let us move forward. What are we going to discuss further? Now we are going to talk about the Raoult's law. What is Raoult's law? My dear students, Raoult's law basically told us, it gave us the idea that now when you have two volatile solute and solvent, how are you going to calculate their vapor pressures? Okay, yes. The partial pressure of any component is proportional to the mole fraction of that component in the liquid solutions. What does this mean, ma'am? We didn't understand. I am going to explain you what does this mean. Now, understand that the container which we took here, and we took A and B. Okay. Now, I know that they both exert in this particular solution. When they both are together, this exerts PA pressure and this exerts PB pressure. Now my dear students, since they are in a mixture and they exert PA and PB pressure, these PA and PB pressures are known as the partial pressure of A, partial pressure of A, and PB is known as the partial pressure of B. Okay. Now, why are we calling it as partial pressure? Because now we are calculating the pressure in the solution. Whenever you calculate the pressures in the solution, you call them partial pressures. And we know that this is not equal to PA naught and this is not equal to PB naught. But my question to you is, if you have moles of A more as compared to moles of B, then the partial pressure of A would be more. Yes ma'am, because you have A more in more amount, so it will exert more pressure. We can say this. Yes ma'am. So my dear students, Raoult actually used this concept and said that PA, that is the partial pressure of A, will be directly proportional to the mole fraction of A, will be directly proportional to the mole fraction of A, which is equal to moles of A by moles of A plus B, right? So basically, or you could say total, right? So basically, Raoult said that partial pressure of A would be directly proportional to its mole fraction. If its mole fraction is more, it will exert more pressure. If its mole fraction is less, it will exert less pressure. Simple and sober. Yes ma'am, we understood this. Similarly, my dear students, if you talk about PB, then that would be directly proportional to mole fraction of B, and that would be equal to moles of B divided by total moles, right? Yes. Now what you have to do is, you have to remove this proportionality and you have to add a proportionality constant. And when you add a proportionality constant, then PA is equal to PA naught XA. This is the expression for PA. PA is given as PA naught XA. Okay, perfect. Now, if you talk about PB and you remove this proportionality, you will get that PB is equal to PB naught XB. Right? Yes, ma'am. This is what is known as the partial pressure of B, which is equal to PB naught XB. If we talk about the total pressure of this container, we know that P total will be equal to partial pressure of A plus partial pressure of B. Yes, now we have calculated from Raoult's law that PA is equal to PA naught XA and PB is equal to PB naught XB. Right? Yes. So let's put those values. PA naught XA plus PB naught XB. Right? Yes. Now what you have to do? You have to just open it. Okay? Yes. Just open it, my dear students. So P is equal to PA naught moles of A by moles of A plus moles of B plus PB naught moles of B by moles of A plus moles of B. Right? Yes. So ma'am, P total will be equal to PA naught NA plus PB naught NB divided by NA plus NB. So this is a different expression which you can use to calculate the total pressure of a mixture of solution. Right? Yes. I hope you don't have any problem in it. Perfect. Now, my dear students, you have derived various expressions. Here is first expression. This is your second expression, right? This is your third expression, and this is your fourth expression. Now, you have to remind your Dalton's law, which you studied in states of matter, right? In case of gases, let us say that Ya is the mole fraction in vapor state. Okay. Similarly, let us say Yb is the mole fraction in vapor state of B, and this is for A. Okay? Yes, ma'am. Now, my dear students, remind the Dalton's law. What did Dalton's law said? Dalton said that if you talk about the partial pressure of A in the vapor phase, partial pressure of A in the vapor phase will be equal to mole fraction of A in the vapor phase into P total. This was the expression by Dalton's law. So I can write it as using Dalton's law. Okay, so I am writing it as using Dalton's law. Okay, Dalton's law. This was discussed in 11th class states of matter chapter. So just go through that again, right? Yes. Similarly, we can say that PB is equal to YB of P total. Okay? Yes, ma'am. If you talk about the expression according to the Dalton's law, which we derived just now, you would say that Raoult's law, PA is equal to PA naught XA, right? And PB is equal to PB naught XB, right? Yes. My dear students, you can equate both because it is also the partial pressure of B, it is also the partial pressure of B. This is also the partial pressure of A, this is also the partial pressure of A. So equate both of them. Equating, you can write that on equating, what can we say? On equating, we can say that YA of P total is equal to PA naught XA. So this is another expression which you will use in your numericals. Similarly, we would say that YB into P total is equal to PB naught XB. So this is the other expression which we will be using in various numericals, right? So this is what we derived from all the knowledge we just gained, right? So this is very important. Just revise it. If you have gone through it, write it on your own. That would make you best in it. Okay, perfect. I hope you understood this. Let's move forward. Now, Raoult's law of vapor pressure, non-volatile solute. Till now, we were talking about A and B. Yes, ma'am. And both were volatile. What if one out of them is non-volatile? Let us say the solute is non-volatile and your solvent is volatile. Now there will be another problem. Yes, ma'am. So let's talk about that. Okay. First of all, here we have to represent it by a formula as well, my dear students. Yes. If you talk about the Raoult's law, you can show this by a graph. You have two components, XA and XB. So you are going to say that XA increases from 0 to XA is equal to 1. Okay. Now XB would be from here. Here XB would be equal to 0 and XB would be equal to 1. Here XA is equal to 0. Okay. Now, if XA is equal to 1, remember the Raoult's law. Raoult's law said that PA is equal to PA naught XA. My dear students, if XA value is equal to 1, if XA is equal to 1, then we can say that PA is equal to PA naught. We can say this? Yes, ma'am. PA is equal to PA naught. Perfect. When XA is equal to 1, let us say this is PA naught. Okay. Now, I am also saying that when you have two volatile components, you have to understand one out of them would be volatile, more volatile, and the other would be less volatile. What is volatility? Volatility is when they have very much of the vapor pressure. Which will be more volatile? Which will have more vapor pressure at the same temperature, right? If we say that out of two components, one is more volatile and one is less volatile, then you are comparing their vapor pressures at a particular temperature. If a component has more vapor pressure at the same temperature as compared to the other, you call it as more volatile. So if I say that A is more volatile, so what do I mean by that? I mean that PA naught would be more than PB naught, okay, at a particular temperature. So I know that when XB will be equal to 1, then PB is equal to PB naught XB. Now when XB is equal to 1, then PB is equal to PB naught. But since A is more volatile, the vapor pressure of B would be less, right? So I would represent it somewhere here. So PB naught. Okay. Now what are you supposed to do? Just show this line, show through this line. As the mole fraction of A is increasing, as we go from here to here, as the mole fraction is increasing, the vapor pressure of A is increasing. Okay? So we can say that this is the representation of PA is equal to PA naught XA. And this is the representation of PB is equal to PB naught XB. I hope you understand this. Yes. Now, whenever you add these, you get P total, which is equal to PA plus PB. You get P total is equal to PA plus PB, right? At this particular point, when the complete pressure is by PA naught, then P total would be equal to PA naught. And when this would be equal to PB naught, then complete pressure would be due to PB naught, right? Yes, I hope you understand this. Just you can write this and then we'll move forward. Okay, let's move forward. What would be the next process? Now, next process is what if you see that out of the two components, one is volatile and one is not volatile. Non-volatile means, again, my dear students, volatility refers to the vapor pressure, right? We would say more volatile, more vapor pressure. Yes. Now, if a component is non-volatile, means that it does not have any vapor pressure, right? Yes. So, we would say non-volatile means no vapor pressure, right? There will be no vapor pressure. Perfect. So, now here it is said that non-volatile solute, if you have a non-volatile solute and you are considering B as your solute, let us consider B as your solute, then we would say that PB naught will be equal to 0. I hope you understand this. Yes, ma'am. Now we are going to calculate the pressures when only and only you have a solvent which is volatile. Okay, perfect, ma'am. So non-volatile solute means PB naught is equal to 0. Volatile solvent is volatile. This means that PA naught is not equal to 0. Okay, this is not equal to 0. Perfect. Let's move forward. Now we are going to talk about the lowering of vapor pressure. Okay. I'll just make you understand this. What happens? Now, just understand this, my dear students, that initially you had one container, okay, and you had only and only A. You had solvent A. If you had only and only solvent A, then, my dear students, total pressure would be equal to PA naught, because it is only the pure A. So vapor pressure would be only because of A, so it would be equal to PA naught. Okay. Now, what I did, I added a non-volatile solute. Now I am saying that add non-volatile solute A. Non-volatile solute A. Sorry, B. Now we are adding a non-volatile solute B. Okay, I know that B does not have any vapor pressure. What will happen? Ma'am, if you add a non-volatile solute, then, my dear students, just see. This was A, you have added B. Yes, ma'am. So B will take some surface on, some place on the surface as well. Yes, ma'am. And some in the bulk as well. Now, if I talk to you about vapor pressure of this solution, now it has become a solution. Yes, ma'am. Now, if I talk about the vapor pressure of this solution, I would say that this would be something P dash. Yes, ma'am. Now, my dear students, if you are considering the vapor pressure at the same temperature, at a constant temperature, right? We would say temperature is constant. Temperature is constant. You have to just imagine it. You just have to imagine it, my dear students, that if your temperature is constant, at some particular temperature, here you have all the particles as A and all the particles are volatile. So they all will contribute to the vapor pressure. Yes, ma'am. So the total vapor pressure would be equal to PA naught. But at the same temperature, my dear students, you have A as well as B, and B is non-volatile. So here A will form some vapor, but presence of B will hinder. Presence of B will hinder because the surface which, on the surface, the position which A should have acquired and then formed the vapors was somewhere taken by the component B as well, which was non-volatile. Yes, ma'am. So less molecules will have opportunity to go outside. Yes, ma'am. If less molecules would have the opportunity to go outside, we can say that this P dash pressure, would be equal to some PA naught XA, that is mole fraction of A, plus PB naught XB. And we know that since B is a non-volatile solute, we know that PB naught is equal to 0, non-volatile solute. Yes, ma'am. So we can say that P dash is equal to PA naught XA. Yes or no? Yes, ma'am. And we can understand this as well, that here P total is equal to PA naught and here P dash is equal to PA naught into some mole fraction of A, and from here we can conclude that P dash is less than the PA naught. Yes or no? Yes. If it was pure A, it would have given you some pressure, but since it is not pure A, B is acquiring some position on the surface and hindering its formation of vapors. That is the reason at that the same temperature, P dash pressure would be less than pure vapor pressure of A, right? Yes. So we can see that what is happening, ma'am, there is some lowering of vapor pressure. Ma'am, there is some lowering of vapor pressure, right? Yes. So now we would say that lowering of vapor pressure. How much lowering is there? Ma'am, initially it was PA naught and now it is P dash. So how much lowering is there? PA naught minus P dash, which is equal to PA naught minus PA naught XA. We can say this? Yes, ma'am. Now just take PA naught common. This would be PA naught minus PA naught would be taken as common, PA naught into 1 minus XA. My dear students, when you have just two components and 1 minus XA would give you, we know that XA plus XB is equal to 1. So, XB is equal to 1 minus XA. We can use this expression. Yes, ma'am. So, 1 minus XA is equal to PA naught XB. Yes, ma'am. And this is lowering of vapor pressure, that is delta P. So delta P is equal to, my dear students, PA naught XB. Where what is XB? Ma'am, XB is the mole fraction of B in liquid phase, right? Yes. Mole fraction of B in liquid phase, where B is your non-volatile solute, right? So we can say that lowering of vapor pressure is directly proportional to the mole fraction of B. The more the non-volatile solute, the more will be the lowering of vapor pressure. Yes, the more the number of non-volatile solute will be present, the more there will be the lowering of the vapor pressure. Yes, so we can consider this. This is a very important expression which you need to understand. Now, if we elaborate this expression, what we can say that here, that delta P is equal to PA naught mole fraction of B by mole fraction of A plus mole fraction of B, right? Now, what you can say that delta P, that is the lowering of vapor pressure, depends on the nature of solvent. A is your solvent. I hope you know that A is your solvent and B is your non-volatile solute. Yes, ma'am. Now, if it depends on PA naught, then we can say that delta P depends on nature of solvent. Yes, it depends on the nature of solvent. Also, it depends on the amount of solute. It does not depend on the nature of the solute. See, there is nothing as PB naught. It does not depend on the nature of the solute. It depends on the amount of solute, right? Yes. So next you can say that delta P depends on amount of solute, amount of non-volatile solute. Okay? Yes, ma'am. Perfect. Let us read further. Okay? These are the conclusions that we have derived. Perfect. Let us see further. Lowering of vapor pressure, my dear students, that is delta P is equal to PA naught moles of A, moles of B upon moles of A plus moles of B. This is your lowering of vapor pressure. Lowering of vapor pressure depends on the nature of the solvent because it depends on PA naught. Yes, ma'am. Number of solvent particles. See, Na naught, Na. Yes, ma'am. It depends on the number of solvent particles and it depends on the solute particles. And it depends on the solute particles because Nb is your non-volatile solute. So, we have concluded that this depends on the nature of solvent only, not on the nature of the solute. Perfect? Yes. Next, my dear students, this is the reason we say that delta P is a colligative property. What are colligative properties? From here we are coming through a new word, that is colligative properties. So my dear students, colligative properties means that those properties which does not depend on their nature. It only and only depends on the amount of that particular substance, right? Yes. If you see that delta P, here delta P depends on the only and only number of moles of B. It does not depend on its nature. So, we say that delta P is a colligative property. It is a colligative property with respect to solute. Why? Because for solute it only depends on the number of moles, but for solvent it is not a colligative property. Why? Because it depends on the nature. It depends on PA naught, so it depends on the nature of the solvent. But for solute it does not depend on its nature. It only and only depends on its moles. That is the reason it is a colligative property with respect to solute, but not with respect to the solvent. Now let us read about colligative properties. Colligative properties does not depend on the nature of solute particles. Okay? Yes, ma'am. Colligative properties are the properties which depend on the number of particles but not on the nature of the particles. Perfect. Lowering of vapor pressure is a colligative property with respect to solute. Yes? Yes, ma'am. Next, my dear students. Now, I know the expression delta P is equal to PA naught moles of A by moles of A plus moles of B. It is moles of B, my dear students. Yes? Perfect. What if I bring this PA naught down? Okay, so I'm doing this delta P by PA naught. This will be equal to moles of B by moles of A plus moles of B. Right? Yes, ma'am. Now, this expression has a different name. This expression, my dear students, has a different name. And this is known as relative lowering of vapor pressure. So delta P by PA naught has a different name and that name is known as the relative lowering of vapor pressure. So now, my dear students, I just want to know that relative lowering of vapor pressure, that is delta P by PA naught, depends on the moles of solute. NB? Yes, ma'am. Does it depend on the nature? No, ma'am. Does it? Now, think about it. Delta P by PA naught depends on the moles of solvent. Yes, ma'am. Here is the moles of solvent. Does it depend on the nature of the solvent? We don't have the pressure expression now. No. So, relative lowering of vapor pressure is a colligative property with respect to the solute and solvent both. Why? Because here this whole expression depends only on the moles of solute and moles of solvent and not on the nature of the solute or solvent. Right? Yes, that is the reason we say that relative lowering of vapor pressure is a colligative property with respect to both solvent and solute. Right? It is a very important observation, my dear students. If some tricky question is to be there, it will be from here. Right? Yes. So mark it as important that relative lowering of vapor pressure is a colligative property with respect to the solute and solvent, but lowering of vapor pressure is a colligative property only with respect to the solute and not with respect to the solvent. I hope you understood this. Perfect, my dear students. Let's move forward. Now we are going to talk about the Henry's law. What is Henry's law? We all like cold drinks. Yes, you admit it or you don't admit it. You like cold drinks. Yes, everyone likes cold drinks, but everyone likes cold drink when it is new. If you have a bottle of cold drink and you just open it, you can hear a fizz noise. Yes, ma'am. And whenever you taste it, it tastes amazing. Okay, I like cold drinks. Perfect. You also like, I know that. Perfect. Now, what if you just pour that cold drink in an open container and leave it for 5 minutes? What will happen? Now, after 5 minutes, when you will drink it, the whole taste is gone. Right? Yes, it would taste like some just sweet water, sweet liquid, right? Yes, the real taste has gone. Why? What was that taste? My dear students, that was the taste of your CO2 soluble in the liquid. Yes, that is the most important part. How is a cold drink made? Let us understand this. Let us consider a bottle. Okay? Here you have the liquid and here let us imagine that you have some gas. Okay? CO2. Now, what happens? You apply pressure on it. And this gas gets soluble in the liquid. And that is the reason your bottle has CO2 soluble in the liquid, and whenever you open it, you get a fizz noise. Why? Because of that soluble gas. Now, my dear students, what does this show? This shows that the more the pressure, the more soluble is your gas in the liquid. Gas will be soluble in liquid under high pressure. If you decrease the pressure, the gas would be insoluble in the liquid. The more the pressure, the more is the solubility. The less the pressure, the less is the solubility. So from here, Henry concluded that whenever you are talking about the pressure of the gas, it is directly proportional to the solubility of gas in liquid. Now, when I said that just pour that cold drink in an open container and leave it, what happened? Initially in the bottle, it was under very high pressure. And later what happened? You just decreased the pressure, atmospheric pressure. The gas came out. It was not soluble in the liquid anymore. And that is the reason you didn't get that taste, right? So you get the taste only and only because of the high pressure maintained in that bottle, right? So from here we can say that pressure of the gas in a liquid is directly proportional to its solubility, right? Yes, perfect. And this was given by Henry's law. Now, what did Henry said? Henry had to remove this proportionality, so he added a proportionality constant. Okay, now solubility can be measured in hundreds of ways, my dear students. It can be measured in hundreds of ways. Again, I said that solubility is also basically what? Here your gas is your solute and liquid is your solvent. Yes, so basically what are you talking about? You are talking about how much of your solute is present in your solvent. So basically you're talking about the concentration terms. Yes, you can use any concentration term. To define solubility. Henry's mostly used the main concentration term, which was mole fraction. Somewhere you will see the expression as molality as well, but in most of the cases you will see the expression of mole fraction. So he said that pressure is directly proportional to the solubility of the gas, and now here we are talking about the solubility in terms of mole fraction, right? The more the pressure, the more will be the mole fraction of solute in the solvent, right? So here I have written that it is directly proportional to the mole fraction of solute. If you increase the pressure, the gas, that is your solute, would have more mole fraction. Right? Yes. Now you have to remove the proportionality. You have to add a proportionality constant. So P is equal to KH into mole fraction of solute. So this was the major expression of Henry's law. Right? Now what you have to understand is when we talk about the day-to-day life, our pressure is constant. Atmospheric pressure? Yes, ma'am. So my dear students, at constant pressure, Now, if I say that constant pressure, that means this value is constant. If, my dear students, this value is constant, I can say that if KH increases, if some gases Henry's constant is more, then its solubility would be less. Yes, ma'am. So you would say that its solubility will be less. Why? Because its mole fraction would be less, na? Because the multiplication of both should be a constant value, and you are talking about a constant pressure. So if at constant pressure some gas KH value is more, its solubility would be less, and if its KH value is less, then its solubility would be more. So the conceptual questions that are made is made by using this concept. So it is very important for you. So understand this concept and use this concept as well. Perfect. We'll do the numerical part as well, so don't worry. You can read all these points. We are going to read it together. First is Henry's law describes quantitatively the effect of pressure on the solubility of gas. Understood, ma'am? Very easy, right? Next, KH does not depend on the pressure. KH does not depend on the pressure. You know that pressure is equal to KH into mole fraction. And you know that, my dear students, KH is a proportionality constant. So if you talk about KH, then that would be P upon mole fraction. If this increases, then this also increases. I know that the more the pressure, the more will be the solubility. So KH does not depend on pressure, right? Yes, it does not depend on pressure, but it depends on temperature. This is an important part. You will mark it. It depends on the temperature, nature of the gas and nature of the liquid. This depends on the nature of the gas and nature of the liquid. So KH depends on three major parts: temperature, nature of gas, and nature of liquid. The more the temperature, the more will be the KH value. The more the KH, the more will be the temperature, the more will be the KH value. Right? Temperature increases, the KH value increases. The greater the Henry's law constant of the gas, the lesser is the solubility. We have understood this at constant pressure. Next, a gas with greater A value, van der Waals constant. Ma'am, what is this? Please explain this. Let us talk about this, my dear students. First, we will understand this, then you will read this line. When in states of matter, you talked about the van der Waals constant A, right? There was a van der Waals constant A. I hope you remember P plus A by V bar square into V minus B bar is equal to RT, right? Yes. So this A, this was your van der Waals constant. Yes, bacha? Yes. Now you know that when A increases, gas liquefaction increases, right? This you read in states of matter chapter. More the A value, more the gas is liquefiable, right? Why is it liquefiable? Because it has more force of interactions. Right? So my dear students, just understand this. Now, if a gas has more A value, it is easily liquefiable. Yes, ma'am. That means the gas can be soluble in water easily. Yes. So the more the A value, more is the soluble, more the gas is soluble. The gas is soluble. Yes, ma'am. And my dear students, more the A value, more the gas is soluble. And I know that P is equal to KH into X. Now, if we take this as constant, this is always taken as constant. And now if this is increasing, if the gas is soluble, then mole fraction is increasing. Then, my dear students, KH value would decrease. So you can say that as the A value of a gas increases, its KH value would decrease and its mole fraction would increase, right? Yes. So this is a very important part from where conceptual questions are mostly made. Perfect. Revise this, my dear students. A gas with greater A value, van der Waals constant, is more liquefiable and more soluble. It will have lower value of Henry's law constant. Perfect. When the temperature increases, the Henry's law constant will increase. No problem, ma'am. We've written this. Perfect, my dear students. In this way, we can say that from here, you can say that now if your KH value is increasing, my dear students, then you can say that solubility would decrease. Yes. So as the temperature increases, KH value increases and the solubility of the gas decreases. Perfect. Very good. Let's move forward, my dear students. Next is ideal solution. What is the ideal solution? A solution which follows the Raoult law. A solution which follows the Raoult law is known as the ideal solution, right? Yes. Now, are there some non-ideal solutions as well? Yes, there are non-ideal solutions, and we are going to discuss about them as well. Perfect. Yes. So, a solution that obeys the Raoult law at any composition is known as an ideal solution. No real solution is ideal. No real solution is ideal, right? Similarly, same to same as ideal gas. A real solution at very high dilution can behave ideally. If you have a solution which is very dilute, it can behave ideally, but it will never be completely ideal solution, right? Yes, perfect. I hope you understand this. Now, we are going to talk about the ideal solutions. First, we will talk about ideal solution, and then we will talk about the deviation from the ideal solution. If you have an ideal solution, so what will you consider? Let us consider that you have some AA solute and you are adding it with some BB solution. Okay? And you are getting a AB solution. Understood? Perfect. Now, you have AA solution, you have BB solution, you get a 2AB solution. Now, my dear students, when will we call this a solution as ideal? We will call this as ideal solution only and only when the force of interaction of AA, BB will be equal to AB. That is the point where we call it as an ideal solution. That is, we say that AA interactions should be equal to BB interactions and this should be equal to AB interactions. Now, you have to consider the bond enthalpies, my dear students. Consider bond enthalpies. Okay? Imagine that all these force of interactions are equal. If all the force of interactions are equal, then what will happen? Ma'am, the amount of energy we used to break these bonds. We will use some energy to break this bond, let us say X, and we use some energy to break this bond as X because we are considering the force of interaction to be equal. Yes, ma'am. Now, when new bonds are formed, energy is released. Yes, ma'am. And since two bonds are formed and their interaction is also equal, so how much energy will be released? Ma'am, 2X. So, what can you say? That total change in energy is 0. Total change in energy is 0. That is, we can say that delta H mixing is 0. Yes. So, for an ideal solution, delta H mixing is 0. This is your first condition. What is the second condition, my dear students? Now, if the force of interactions are equal, so if you consider for AA plus BB gives you 2AB. Now, if you consider that this is some V liter volume and this is also some V liter volume, now when you added all these together, you will get 2V volume. Since their interactions are equal, yes ma'am, you took their interactions to be equal. So, if they are present in some V volume and they are present in some V volume, you will get 2V volume. If you take the total volume change, delta V mixing, you will say that ma'am, total volume change is also 0. Yes. So, this is an ideal solution. For an ideal solution, delta V mixing is also 0. Okay. So, now you can see this. The energy absorbed when solvent-solvent bonds and the solute-solute bonds are broken exactly equal to energy released when the solute-solvent bond is formed. Similarly, delta V mixing, you can understand this concept as well. Now, we will talk about the entropy factor. What is the entropy factor, my dear students? It talks about the randomness. Now, what is the meaning of randomness? Imagine you have AA balls. You have some AA balls. Okay. Now, imagine you have some BB balls. Here is B, here is B. What did you do? You just took them and added to a single container. Okay, so you took them and you added them to a single container and you got A and you got B. Okay, now consider this container. Does this have any randomness? If you have a container and you just put your hand, you will always get A ball. Always, there is no randomness. Now, when you talk about B container, you take out some ball, you will always get a yellow ball, which is B. But when you talk about their mixture, bacha, now when you will take out some ball, there will be randomness, there will be a possibility that you get a green ball or you get a yellow ball. Yes, ma'am. And entropy is the measure of randomness. Entropy is the measure of randomness. The more the randomness, the more is the entropy. So we can say that always delta S will be a positive value. Always delta S will be a positive value. Yes, ma'am, because there is no entropy here, but there is a entropy here. Randomness. So you can say that delta S is measure of randomness. Okay, so what is it? It is the measure of randomness, and it is always positive because there is randomness, but in the reactant side there is no randomness, right? Yes. So now let us understand this. Delta S mixing, you have white ball, yellow ball. In solution, we have two different types of particles. In the pure solvent, ideal mixing is a spontaneous process and it is an exam entropy effect. Okay? The more the entropy, the more spontaneous is the process. Perfect. Next. Now, deviation from Raoult's law. What will happen, my dear students? If you talk about deviation, then what are the possibilities? You can have positive deviation. You can have positive deviation and you can have a negative deviation. Okay? Okay. So now we are going to talk about these. First, we have to talk about the examples, my dear students. We've not written examples. If you talk about ideal solution examples, then most of the cases, they are similar. For example, if I talk about benzene, it is represented like this, and toluene. It is an example of, my dear students, ideal solution. Okay? In your NCERT, only and only the examples given in your NCERT are important. Don't memorize any other thing, just memorize the examples given in your NCERT. Only and only that is important. Okay? Or it can be N-hexane plus N-heptane, right? This is also an example of, ideal solution. Also, you can say that diethyl ether and dimethyl ether. Okay, so this is also an example of what? Ideal solutions. Okay, now we are going to talk about the deviations, that is positive deviation and negative deviation. What is positive deviation and negative deviation? Now just consider about it. Consider, till now, whenever we talked about the solution, we talked about their interaction. Now, what are the possibilities? Maybe after mixing, interaction is weak, or maybe after mixing, interaction is stronger. That is only the main reason which decides that it will be a positive deviation or a negative deviation. Okay, and consider it. If you say that AA plus BB gives you 2AB. Okay, yes. Now, what if, my dear students, that AA interactions and BB interactions are stronger than AB interactions, right? Yes. Now imagine, my dear students, what will happen? Ma'am, if before mixing, my dear students, before mixing, your interactions were stronger and later your interactions became weaker, what will happen? The particles have more possibility of going outside. Yes, they will have more pressure. Yes, they can easily go out because the interactions are weak. Yes, ma'am. So if I ask you for a solution, the total pressure, let us say that the total pressure was PA plus PB, right? Then for a positive deviation, my dear students, what will happen? Now particles have more possibility of going outside, right? After mixing. Why? Because first their interactions were strong. First they were very close to each other, but later they can go anywhere because their interactions are weak. So we can say that the pressure, if we say that here the pressure is P total dash and here the pressure is P total, then my dear students, P dash will be always more than P total, right? So for a positive deviation, my dear students, total pressure would always be more than the Raoult's law calculated ideal pressure. The pressure which is calculated for an ideal solution, for a positive deviation, the total pressure would always be more than that. Right? I hope you understand why. Because the later interactions are weaker, so they can form more vapors, and that is the reason total pressure would be more, and that is the reason we say it as positive deviation. Similarly, now you can understand the negative deviation also. What will be negative deviation? Again, AA plus BB will give you 2AB. Right? Yes, ma'am. Now what will happen? Now AA interactions will be equal to BB interactions, and the interactions later would be stronger. Now, my dear students, if later interactions are stronger, then what can you say? That the pressure which you calculated according to the ideal solution, the pressure here will be less. Why? Because after mixing, after mixing, what will happen? After mixing, the molecules will stay closer, and that is the reason their vapor pressure would be less, right? Yes. So if we calculate here as P total and here as PT dash, we will say that PT dash will be less than P total, and this will show you negative deviation, Clear? Perfect. Very good. Let's move forward. आगे देखते हैं. What will happen? Positive deviation. I hope you got the major idea. Now we will just discuss the points. What is it saying? If one component shows the positive deviation, the other component is bound to show positive deviation. Okay, if one is positive, then the other is positive. We understand this. No problem. Next, my dear students, if the solute-solvent interactions after mixing decreases, now, my dear students, it is talking about the interactions. That is, it is saying that AB interactions are less than AA interactions or BB interactions. Okay? If the solute-solvent interactions after mixing decreases, more molecules will move into the vapor phase. I hope you understand that more molecules would move into the vapor phase, contributing to the more pressure. And that is the reason the pressure of this side would be more than the pressure of this side. Right? Yes. The energy absorbed to break the solvent-solvent and solute bond is greater than the energy released than weaker solvent. Now, what you have to imagine here that for positive deviation, my dear students, always delta H mixing will also be positive. Why? Because what do? You, let us write it here. AA plus BB gives you 2AB. Now, see, you provided some energy, that is delta H energy you provided to break this bond. You provided some energy to break this bond. But this bond is a weaker bond. So the energy which it will release in the negative form will be less. Right? So what can you say? That the negative part of the energy is less, but the positive part of the energy is more, right? Here also positive energy because you are providing, here also positive energy because you are providing. So the positive part is more and negative part is less. So overall delta H mixing will be positive. Yes, ma'am. Similarly, now you can consider the volume wala part as well also. For the volume part, what can you say? My dear students? Ma'am, here the interaction is weak. So it will occupy more volume. So V final minus V initial would be a positive value. Yes. So my dear students, for this case, delta V mixing is also positive. And if you talk about the entropy, beta, entropy is always positive because after mixing there will be randomness. Before mixing there will be no randomness. So delta S, that will always be a positive value. So for a positive deviation from ideal solution, you will have delta H mixing positive, delta V mixing positive, and delta S is always positive, right? Here are some examples which you need to understand. Acetone and hexane, ROH and cyclohexane, and H2O and ROH. I hope you understand this. Perfect. Let's move forward. Now we are going to draw the graph for this. Okay? Yes, ma'am. How are we going to draw a graph, my dear students? Again, you will consider this like this. You have XA. So XA is equal to 1, XA is equal to 0. XB, you have XB equal to 1 and you have XB equal to 0. Okay. Now, let us consider that A is more volatile. Now, if A is more volatile, then ma'am, PA naught is more than PB naught. Okay, perfect. So, here is PA naught and let us say here is PB naught. Yes, now add this and add this. What is this? This is if it was an ideal solution, but it is showing a positive deviation. And in positive deviation, we all know that in a positive deviation, we all know that pressure is more. Why? The interactions are weaker later, right? So the value would be something like this. It would be something like this. And if you talk about the total pressure, this was the total pressure. My dear students, its total pressure would also be more, right? Yes. So this would be the plot for a positive deviation of a solution from the Raoult's law. Similarly, we can talk about the negative deviation as well. What will be there? Ma'am, delta H mixing would be negative. Yes, bache. Similarly, the same concept, you have to understand this. Now, if you talk about delta V mixing, my dear students, it will also be negative. But delta S, entropy, will always be a positive value because after mixing only you get the randomness, right? Yes, solvent-solute interactions after mixing is stronger than solute-solute or solvent-solvent interaction, right? In this case, we know that after the mixing interaction becomes stronger. After the interaction, if interaction is stronger, then you need to provide more amount of energy to break it. That is, if it breaks, it gives more amount of energy, and if it gives more amount of energy, then that is a negative value. So your delta H mixing is negative. If you talk about the volume, now the force of interactions are stronger. The final volume will be less and the initial volume would be more. So V final minus V initial would be a negative value. Yes, ma'am. And entropy, we understand this. Perfect. Yes. Here is the statements. The energy absorbed when solute-solute and solvent-solvent bonds are broken is less than the energy released when solvent-solute bond is broken. Delta V mixing is negative. Molecular attractions increases after mixing. Molecules are drawn closer to each other. As a result, volume decreases. The delta S mixing will be positive. I hope you understand this because of the randomness. Okay. Now, if any volatile solute, stronger electrolyte is dissolved in H2O, it shows the negative deviation. Examples are here which are important. You just need to understand, you need to memorize only and only these examples. Clear? Very good. Perfect. Let's move forward, my dear students. Now we are going to draw the graph. I hope you can draw the graph. So first, pause the video and draw the graph yourself. Okay? Perfect. Now we are going to draw the graph, my dear students. Again, the same process. We will have XA. XA is 1. XA is 0. XB is 1. XB is 0. Again, I am considering A is more volatile. Okay. If A is more volatile, then PA naught is more than PB naught. Now what will happen? Ma'am, here it will be PA naught and here it will be PB naught. Okay. According to ideal solution, this should be like this. Okay, but this is not like this. We know that for a negative deviation, the total pressure that is considered would be less than the ideal solution. So the graph would be something like this. Okay. So this is the plot for your negative deviation. This is the plot for your negative deviation. I hope you understand this. Perfect, my dear students. Next is elevation of boiling point. Now we are going to talk about the colligative properties, the properties that only and only depends on the amount of your solute, right? Yes. How are you going to understand this? Just remember that we are going to plot a graph. We are going to plot a graph between pressure and temperature. Okay. We are going to plot a graph between pressure and temperature. Perfect. What is the graph between pressure and temperature, my dear students? PV is equal to nRT. If you have V constant, R constant, R constant, then P is directly proportional to T. So it should be a straight line. It should be a straight line, right? Yes. So I just did this. Okay. Now, my dear students, I want to know that I have drawn two lines. One is for pure solvent A and one is for a solution which has a non-volatile solute in it. That is, let us consider, you have two solutions. Here you have pure A and its pressure is PA naught, okay? And the other is A plus B, where B is non-volatile, okay? So it is a solution. And let us say its pressure is PA naught and let us say its pressure is P total. Its pressure is P total. So now, how are you going to understand this? Okay? Let us see. I know very clearly that if I have at a constant temperature, at a particular temperature, if I see, then I can say that pure A will exert more pressure than the solution. Why? Because the non-volatile solute will cover some surface and will hinder the formation of vapor from A. So I can say that PA naught will always be more than P total at constant temperature. At some constant T temperature, always PA naught will be more than P total. I have to find that from these two lines which is the pressure of solution and which is the pressure of solvent. So what will I do? I will take some constant temperature T. Let us say some constant temperature T. I took this. Yes. Now, corresponding to this, I saw that this is some PA pressure, and corresponding to this, I saw this is some PB pressure. If I see, I can say that PA is more than PB. Call it as P1 and P2. P1 and P2. Okay. I can say that P1 is more than P2. At some constant temperature, if P1 is more than P2, I know that at constant temperature, PA naught will always be more than P total. So I can say that PA is PA naught and P2 is P total, right? So this pressure, the P1 corresponding pressure would be for pure solvent. So I would say that this is pure solvent A and this is the solution, that is A plus B, right? Yes. I hope you understand this because this was a very important part, right? Yes. If you did understand this, now we are going to talk about the boiling point. Okay. Just let me draw it and then we'll talk about it. Perfect. Now, my dear students, if you talk about the boiling point, right? Because we are talking about the elevation and boiling point. First, you have to understand that what is boiling point. Boiling point is the temperature where the vapor pressure inside the container is equal to the atmospheric pressure. Whenever in a container, the vapor pressure becomes equal to the atmospheric pressure, that particular temperature would be called as boiling point. Okay, yes ma'am, I understood this. Now, if you have a container like this, right? Now, you know that vapor pressure of PA naught is more than P total at some constant temperature. At some T temperature, you are just increasing the temperatures. At every temperature, you know that PA naught will be always more than P total. Yes, ma'am. So, what can you say? What can you say, my dear students? That PA naught will be equal to the atmospheric pressure before P total will be equal to the atmospheric pressure. Yes. See, if you have one atmospheric pressure, that is your outside pressure. You are increasing the pressure. You are increasing the pressure by increasing the temperature. You know that always PA naught will be more than P total. Yes, ma'am. Then at some T temperature, PA naught will be equal to the atmospheric pressure beforehand. P total becomes equal. Yes, ma'am. Yes, ma'am. Let us say this is 0.7 atmosphere initially and this is 0.5 atmosphere initially. If you increase the temperature, my dear students, if you increase the temperature and your atmospheric pressure is 1 atmosphere, which pressure will become equal to the atmospheric pressure first? PA naught? Yes, ma'am. And that T temperature where PA naught will be equal to 1 atmospheric pressure will be known as its boiling point. Let us say the boiling point of P total is TB naught. TB naught, right? Now, my dear students, you are increasing the temperature, right? Yes, TB naught will come first, and then at some higher temperature, this P total will be equal to 1 atmosphere, right? Let us say the boiling point for this is TB. So, can I say that TB naught will always be less than TB? Right? Because you need to heat the solution wala part more. To make the vapor pressure equal to the atmospheric pressure. Yes. So, the temperature at which this pressure will be equal to this will be more as compared to TB naught. Yes, ma'am. So, my dear students, we say that TB naught will always be less than TB. Right? Yes. Now, from here, what can you say? From here, you can say that always your temperature, the solution's boiling point will be more, right? Yes. So if I ask you that delta TB is equal to, what will be delta TB? Ma'am, solution wala part is more. So ma'am, TB minus TB naught. So my dear students, what can you say? Is it elevation and boiling point? Is it that whenever you add more solute, boiling point increases? If you add more solute, boiling point will increase even more. You add more non-volatile solute, boiling point will increase even more. So what can we say? That the change in, that is the elevation in boiling point depends on the amount of non-volatile solute you are adding. Yes, ma'am. So my dear students, we say that delta TB, which is equal to TB minus TB naught, is directly proportional to the molality of the solution, that is moles of solute divided by the mass of solvent in kg. And this is experimental, that they used the molality term for the expression. Okay, so from here we can say that delta TB is directly proportional to molality. Delta TB is equal to Kb into m, where, my dear students, this m is the molal elevation constant, or it is also known as ebullioscopic constant, and this is specific for all the solvents. For different solvents, Kb values would be different. For example, if you talk about water, then Kb value for water is 0.52 kilo kg mole inverse, Kelvin kg mole inverse, Kb for water. Okay, but in most part of the questions, you are given this value. Clear? Yes, ma'am. I hope you understood this part, that how elevation and boiling point takes place, and you are given thousands of numericals on this particular part, which we will discuss in our coming session. Right? Yes, I hope you understood this, my dear students. So now you can read this. Boiling takes place from whole liquid, and boiling point of a given pure liquid is constant only when external pressure is constant. Yes, the whole liquid is completely covered to vapor and the temperature remains constant under a constant external pressure. Clear? Very good. Let's move forward. Now we are going to talk about depression and freezing point. It is exactly same as we have discussed about elevation and boiling point, my dear students. Now how you have to understand this depression and freezing point, I'll give you a live example. Whenever in snowy areas like Oli or Mussoorie or any snow where snowfall takes place a lot, many a times what happens, due to heavy snowfall, the roads are blocked, right? So how are we going to melt that snow? What happens? We have to decrease its freezing point. We have to decrease its freezing point. How do we decrease its freezing point? What do we do? How do we melt it easily? We add salt on it. Salt is a non-volatile solute. What is salt? Salt is a non-volatile solute, and that non-volatile solute actually, what does it do? It helps in melting the snow at a higher temperature. Now I am going to tell you what is depression in freezing point, right? If you talk about depression in freezing point, let us say that TF naught is the freezing point of pure solvent. Okay, what is it? It is the freezing point of pure solvent. Okay, yes ma'am. And let us say TF is the freezing point of solution. If they are talking about the depression in freezing point, my dear students, then depression in freezing point means that your TF naught will be more than your TF. That is, every time you add solute, your freezing point will decrease. Every time you add solute, your freezing point would decrease, right? Yes. So if you talk about delta TF would be equal to TF naught minus TF, and this will be directly proportional to exactly same as elevation and boiling point, directly proportional to molality. That is, the more the non-volatile solute you are going to add, the more will be the depression in freezing point. The more would be the depression in freezing point, right? Yes. So TF naught minus TF will be directly proportional to molality, and from here we can say that, delta TF is directly proportional to molality. Delta TF is equal to KF into molality. What is KF, my dear students? It is the molal depression constant. It is known as the molal depression constant, and it is also known as the cryoscopic constant. It is also known as the cryoscopic constant. Every liquid, every solvent has a specific KF value. For example, KF value for water is 1.86 kilo Kelvin kg mole inverse. Okay, perfect. So this is how you calculate the depression in freezing point. This is how you calculate the depression in freezing point, and this is used in various numericals which we are going to discuss. Perfect. Yes. So I hope you understood this part. When a non-volatile solute is added to pure solvent, freezing point decreases, and this is known as the depression in freezing point. Perfect. Now we are going to talk about the osmotic pressure, bacha. What is osmotic pressure? Let us understand this. What happens is, now consider you have a container like this and you have a semi-permeable membrane. This is your semi-permeable membrane. Okay, what is semi-permeable membrane, my dear students? Semi-permeable membrane is a special type of membrane which allows some specific things to go through it but does not allow the other things to go through it. That is, let us say if we have a solution, then it will allow the solvent to pass through it, but it will not allow the solute to pass through it. That is, semi-permeable membranes are very specific in what size of particles are going through them. Okay, yes. Now consider that you have here pure liquid and here you have a solution, that is A plus B. Okay, now whenever you have this type of containers, you have pure liquid and you have pure solution, then always the movement is from high pressure to low pressure, from high concentration, high amount to low amount. Now if we see that we have pure liquid here and here we have solution, so I can say that it is pure liquid of A. I can say that the volume of A is more here and in solution it is less, as there is some amount of B also present. Yes ma'am. So when the movement happens, what will be? It will be like this. This movement will take place. Okay, and since the semi-permeable membrane allows the movement of solvent will move from here to here. But if you talk about the solute particles, that is the B particle, that is more in the solution and not in the pure wala part. So the solute should move from here to here, high value to low value. But since semi-permeable membrane does not allow the solute to go through it, that is the reason B does not go. Right? Yes. So now we can say that A is moving to the solution side. Okay. Yes, my dear students, this is moving to this side. Now, when your pure liquid is moving to the solution side, it is exerting some pressure. It is exerting some pressure. And that pressure is known as the osmotic pressure. That pressure is known as the osmotic pressure. Okay. This is one type of definition which you call that what is osmotic pressure. When a pure liquid moves to the solution side, some pressure is exerted and that pressure is known as the osmotic pressure. But another definition is if you open this area and you apply some P pressure Now, when it is exerting like this, there is some P pressure, right? If you apply some pressure from this side, that is equal pressure. You are applying some sort of pressure that you can stop this movement. You can stop this movement. When can you stop this movement? Only when you apply the pressure which is equal to the osmotic pressure, right? Yes. So you have a different definition for osmotic pressure as well. The pressure applied to stop the movement of pure liquid to the solution side is also known as the osmotic pressure. It is a pressure. So see, we know that PV is equal to nRT. So P is equal to N by VRT. So pressure is equal to CRT. Here this P is represented by pi is equal to CRT. This is your osmotic pressure. Bacha, this is your osmotic pressure. So this is the expression for osmotic pressure. I hope you understand this. Perfect. So this is what is known as osmotic pressure. The pressure exerted by this pure liquid movement to the solution side is known as osmotic pressure. First, the second definition is it is equal to the pressure exerted so that you can stop the movement of pure liquid to the solution side. Perfect. Let us read it. When membrane is permeable to solvent particles but impermeable to the solute particles, they are called semi-permeable membrane. Solvent can pass through but solute can't. Perfect. It is talking about the semi-permeable membrane. Osmosis. Now you have to understand the meaning of osmosis. I have told you. Movement of solvent molecules through the semi-permeable membrane from the pure solvent side to the solution side, from less concentration solution to more concentration solution. This is known as osmosis. Osmotic pressure is the hydrostatic pressure built up on the solution side due to the osmosis from the pure solvent side to the solution side. Clear? Perfect. A concentration solution containing non-volatile solute will have a greater osmotic pressure but lower vapor pressure. Right? Yes, I hope you understand this and I hope you understood the whole osmotic pressure concept. Perfect. Next, alternative definition of osmotic pressure is exact pressure to be applied on the solution side. The pressure you applied this side. Yes, the exact pressure to be applied on the solution side in perpendicular direction so as to stop the osmosis from the pure solvent side. Now, my dear students, if in this container where you have pure solvent A and you have solution, you apply some P pressure which is more than the osmotic pressure. What will happen? If you apply some P pressure which is more than the osmotic pressure, your solution will start moving towards the pure solvent. And since the semi-permeable membrane will allow only the solvent movement, the solute will not move and the solvent from the solution side will move. You understand that concept? Yes, ma'am. So this process will be known as reverse osmosis. When you apply more pressure than the osmotic pressure, the solvent from the solution will start moving, and that is known as the reverse osmosis. And this is how your water in RO system is purified, right? So read this. If the pressure applied on the solution side is greater than the osmotic pressure of solution, the solvent will flow from the solution side to the solvent side, and it is called as the reverse osmosis, right? Yes. So I hope you understood this. Two solutions having same osmotic pressure, my dear students, are known as isotonic solutions. If you have two solutions which have the same pressure, right, and if you add them here, let us say this is solution 1 and this is solution 2 and both have the same pressure, then it is known as isotonic solution. Then such solutions are known as isotonic solutions, right? Yes. So I hope you understood this, and with this we came to the end of our session. This is all about the solutions chapter, and I hope you understood this. So first let me write thank you, my dear students. Yes, I'll write thank you. Thank you so much for being here, for understanding the whole chapter, and please do let me know in the comment section how was your experience with this particular session. We will be bringing more such sessions. We will be bringing a practice session for solutions chapter as well. Till then, you have to revise whole concept. Thank you so much. All the very best.